Hey science students, and welcome back to another lesson with me, Leslie, from Tesla Tuition Videos. In today's lesson, we will be looking at series circuits and how these types of circuits affect variables such as current, potential difference, and resistance. Okay, let's get to work. Right, so now that we've had a look at current, potential difference, and resistance in detail, now we want to have a look at how these three variables are affected by whether we have a series circuit, a parallel circuit, or even a combination circuit. Now, what makes a circuit a series, parallel, or combination circuit is the way that the resistors are connected. So it's the connection of resistors that makes the circuit either a series or parallel circuit. Let's first take a look at our series circuit, which is arguably the more simple of the two. So what is a series circuit? Well, in a series circuit, you only have resistors in series, which means they are connected on the same main pathway. Now, I'm also going to use this as an opportunity to teach you a few tips and tricks for interpreting a circuit diagram. Now, I've drawn a circuit diagram here in black, and when learners get circuit diagrams in a question, before they even read the questions, they should first work their way around the circuit in the direction of conventional current and quickly just identify the components that they see in the circuit. So just to show us current flowing in a circuit, which usually doesn't get shown on a circuit diagram, I'm just going to indicate in purple a few arrows showing the direction of conventional current, which, as we said earlier, is the direction of current from the positive terminal of the battery. This is our cell or battery here. The longer line is the positive terminal. The shorter line is the negative terminal. And conventional current flows from the positive terminal all the way around the circuit, like so, to the negative terminal, just like that. Now, in my circuit, I do have a switch that is closed, which is why current is able to flow. If the switch is open, it means there's no current flowing in the circuit. Now, when you're trying to see the pathways that current flows in a circuit, it is recommended that you ignore any pathway that has a voltmeter on it. So again, voltmeters have very high resistance, which is why we always connect them on their own parallel branches. Because if I were to put any of these voltmeters on the main pathway, then the high resistance of the voltmeter would completely disrupt the current in the main pathway. So by putting it on its own parallel branch, there is still an alternative pathway for current to flow undisturbed. By the way, when you've got more than one ammeter or voltmeter, they typically use specific subscripts, little letters or numbers, to distinguish the different ammeters and voltmeters. So I have a voltmeter over my battery here. This is often called V1 if there's multiple voltmeters, but I'm choosing to call it VB, B for battery. This is the voltmeter over the battery. Now, as we move around our circuits in the direction of conventional current, I've got an ammeter over there on the main pathway, ammeter A1. And then as we continue around, here's a resistor R1. Resistor R1 has a voltmeter over it, V1, but remember, virtually no current flows in your voltmeters. And that voltmeter V1, I could have drawn it underneath or above resistor R1. Both would be correct. Then as we continue to move, here's another ammeter A2. Then the pathway bends. Here's another resistor R2. R2 has a voltmeter over it, V2. And here's another ammeter A3. There's my switch that is closed, and there we are back at the negative terminal of the battery. Now, how do I know that this is a series circuit? Because my two resistors R1 and R2 are on the same pathway, which is also the main pathway, And importantly, for a series circuit, the main pathway does not split into any parallel branches. Again, ignore any branch or pathway with a voltmeter on it, since virtually no current will flow in that pathway anyway. Now, some students might look at this and think, oh, but R1 and R2, they're on different pathways because the main pathway bends. They're actually still on the same pathway. It does not matter if your main pathway bends. It is still the same pathway, and R1 and R2 are series resistors. They are on the same main pathway as each other. R1 and R2 are in series. Okay. Now, also bear in mind that just because there isn't maybe an ammeter or voltmeter somewhere in your circuit doesn't mean that there isn't a current or voltage that can be measured in the circuit. Some students have the misconception that there'll only be a voltage or current somewhere if there's an ammeter or voltmeter to measure it, and that's not true. Currents and voltages or potential differences can exist in different places even if there isn't an ammeter or voltmeter to record them. So just bear that in mind. Okay, so now that we have looked at our circuit and we know where current is flowing and we know that resistor R1 and R2 are on the same pathway, the main pathway, now we can look at how things like current, potential difference, and resistance get affected in a series circuit. Let's start with current. Now, what learners must know is that current is equal at all points in a series circuit. And obviously, I'm not including any branch with a voltmeter on it. This, where my finger is moving, this is the main pathway. And current is equal at all points on the main pathway in a series circuit. And what that means for us is that the current measured by A1 is equal to the current measured by A2, which is equal to the current measured by ammeter A3. Current is equal at all points in a series circuit. And that means that resistors in series are receiving the same total amount of current in that main pathway. Sometimes it's useful with electric circuits to think of the flow of current as being like the flow of water. If there's one main river and it doesn't split into smaller streams, then the strength of the water flowing is the same at all points in the same river pathway. So using water as a metaphor for current is often quite helpful. Okay, so now let's move on to potential difference or voltage. Now, resistors in series are said to be potential difference dividers. This is a common term for resistors in series. They're potential difference dividers. And what that really means is that resistors in series share the battery's total voltage. So bear in mind, the total EMF or potential difference is the one measured over the battery. So the biggest potential difference is the one over the battery. And resistors in series are going to be sharing portions of the battery's total voltage or potential difference. That means the voltage over my first series resistor, V1, plus the voltage over my other series resistor, V2, added together, that would give me the total voltage over the battery, VB. And that's why I said here, V1 plus V2 equals VB. So, in other words, if you add the potential differences over all series resistors in the circuit and you add them together, the sum of those voltages will be equal to the voltage or potential difference over the battery. Now, learners must be very careful and not assume that these series resistors share the battery's voltage equally. They don't always. Now, if the resistors in series have identical resistance, and that would happen if they're identical resistors, then with the same resistance and the same current, they will have equal amounts of potential difference over them. But if resistors in series like R1 and R2, if they've got different values of resistance, then they will have unequal potential differences over them. But it would still be true that the sum of the series resistors' potential difference, like V1 and V2, would add up to the battery's total voltage, in this case, VB. So in conclusion, resistors in series divide up or share the battery's total potential difference. Right, now coming to resistance. Now, it is an extremely common exam or test question to calculate the total, also known as the effective resistance of an electric circuit. Now, in a series circuit where you only have resistors in series, the total or effective resistance you can refer to as RS. RS is the total series resistance. And there's a formula to work out series resistance, which is printed on formula sheets. This is the formula. RS equals R1 plus R2, and then there's a little dot, 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 because, as the theory goes, you can add any number of resistors in series. So with series resistors, to get the total or effective resistance of the circuit, all you have to do is add the different values of your series resistors together to get the total or effective resistance in series, which we've symbolized as RS. We will also be using the Ohm's law formula to calculate various resistances, potential differences, currents, etc. What I will just say is that you always need to use values of V, I, and R that go together. For example, if I wanted to calculate specifically V1, the potential difference over R1, I would need to use the current flowing in R1, which is the same at all points of the series circuit, but I would also need the specific resistance of resistor R1. So you need the current in R1 and the resistance of R1 to calculate the potential difference over R1, which is V1. So always use values of resistance, potential difference, and current that go together for a certain calculation. Okay. That brings us to the end of today's lesson on series circuits. Head over to our website for our full-length science videos.